And now we're going to talk about, instead of glomerular-tubular balance, we're going to talk about tubuloglomerular effects. The first effect I want to talk about is autoregulation. This term should not be new to you. This is the same phenomenon that occurs in other places, other blood vessels in the body. The purpose is to maintain kind of pressure within a wide range of larger arterial blood pressures within the whole body. In the kidney, autoregulation's purpose is to maintain blood flow and glomerular filtration rate, even in the face of big changes in body-wide blood pressure. So the stabilizing ability of blood flow is also apparent in the brain and the heart. Very important there. You want to keep normal kind of stable pressures, particularly in the brain, so you don't start damaging things. And the same thing happens in the glomerulus. You have those delicate glomerular capillaries, and if you increase the pressure so much beyond what it can handle, you're going to essentially blow them out and damage them, and that is bad news for your kidney function. So autoregulation is mediated by a couple of things. In the face of increasing pressure, you will, as a result, have increased resistance to that pressure. That is the local reflex, which is mediated by vascular smooth muscle cells called the myogenic reflex. And you also have some physiological feedback. Physiological feedback occurs via the juxtaglomerular apparatus, and this is what we call, in renal physiology, tubuloglomerular feedback. So I kind of foreshadowed the juxtaglomerular apparatus earlier on in this lecture in the effects that sympathetic stimulation has on JG cells, and we'll talk about that next. This image over here on the right is showing increased renal arterial pressure, and you'll see that within a range, a certain range here, that GFR is maintained stable. Overall renal blood flow is maintained stable. And it does so by changing, auto-changing either the afferent or the efferent arteriolar resistances during those phases. So if you have skyrocketing blood pressure, you want to try to affect a hemodynamic change in your arteriolar, either the afferent or the efferent arteriole, to kind of counterbalance that, to maintain a stable GFR. Of course, autoregulation has its limits. At very extremely high pressures and very extremely low pressures, it no longer works. This is the myogenic feedback reflex. This is that kind of auto reflex where blood vessels resist stretch during periods of high blood pressure. There is, a second or less delay in vessel contraction. This is mediated through various calcium signaling methods that I won't particularly go into right now. And one of the effects, very important, is you could get afferent arteriolar constriction at the same time as efferent arteriolar dilation. And this is meant to kind of protect the glomerulus during times of really high blood pressure. Now, the slightly more complicated feedback mechanism of tubuloglomerular feedback is made up of the system called the juxtaglomerular apparatus. The JG apparatus is consisting of the macula densa cells themselves, the juxtaglomerular or the granular cells, and then extraglomerular mesangial cells, sometimes called lasis cells. So the juxtaglomerular apparatus has three components: the macula densa cells of the distal tubule, the juxtaglomerular cells, and then extraglomerular mesangial cells. So these extraglomerular mesangial cells live kind of outside the glomerulus, but kind of associated with it. Its purpose is to sense tubular concentrations of sodium chloride in that distal tubule. If it is sensing a change from a deviation from normal, either up or down from what it would expect, this initiates a signaling cascade that feeds back from the macula densa to the JG cells to the glomerulus, with the purpose to adjust arteriolar resistance as needed, either up and down. And the signaling between the macula densa cells and JG cells, its purpose is to also maintain constant sodium delivery to the distal tubule and therefore constantly regulated GFR. And then also tubuloglomerular feedback initiates the renin-angiotensin-aldosterone reflex, which you've already learned about previously from endocrinology. Now that we've talked about the big picture of what tubuloglomerular feedback does, let's talk about how tubuloglomerular feedback works, essentially the mechanism, and that is what this slide is going to depict. Now, this is the most kind of straightforward and basic and simplified version of this that can be presented, and this is absolutely enough information to set you up for cardiopulmonary renal 2 and associated pathologies next year. The steps by which TG feedback work are outlined over here on the left. This is kind of a stepwise series of events, and then the graphic is over here on the right. So let's start with the scenario where you increase sodium chloride delivery to the macula densa. Now, before we get into this, what are things that can deliver increased amounts of sodium chloride to the macula densa? Well, that can be because maybe GFR has gone way up and sodium chloride is simply being flushed through the nephron faster and faster. It can be due to pressure. It can be due to increased concentration of sodium chloride within the tubular fluid, such as if you have eaten a lot of sodium in your diet, for instance. So anything that increases delivery of sodium chloride to the macula densa is what kicks off tubuloglomerular feedback. So here's the steps that take place. The macula densa cells are here in these boxes. These are representing those epithelial cells. These are the epithelial cells of the distal tubule. The tubular fluid side is over here, so this is where the primitive urine would be flowing. The blood side is over here on the right, and that's what this kind of red line right here is depicting. That's supposed to be a blood vessel where fluid, upon reabsorption, would travel in this direction from left to right. So from the tubular fluid side to the blood side in this directionality from left to right for reabsorption. Now, step one, we have more sodium chloride being delivered to the macula densa. So it's flowing down the tubule. When it encounters the co-transporter that you'll learn about in more detail in the renal tubular transport lecture, when it encounters its transporter, which in this case is called the NKCC2, that was kind of a wobbly NKCC2 there, that is representing this circle. What this means is co-transported at the same time is one sodium chloride, one sodiums, two chlorines, and one potassium molecule, all co-transported into the cell at the same time. So we have more sodium chloride being delivered to this area of the tubule. More sodium chloride gets reabsorbed. So now we're on step two. More sodium chloride has been reabsorbed into the macula densa cell. So now we have sodium chloride, we have potassium, we have lots and lots of sodium, lots and lots of sodium. All of this is building up inside the cell. Now there is a series of biochemical and molecular steps that take place between step 2 and 3 here that we're not going to go into. What I'm going to get at is that the more sodium chloride that is released, there is a next step release of ATP and or ADP. When this happens, ATP is generated or it is processed down to ADP. Either way, they can be released from the basolateral side of the cell. Let's just ignore what happens to the sodium and the chloride and all that at this time. Right now, there is a jump from sodium chloride reabsorbed, and now we've generated extra ATP or ADP. It's reabsorbed across the basolateral membrane. So this side is the basolateral side. This is the apical side. And now it's floating out here in the kind of the juxtaglomerular apparatus region. Upon its movement into this area of the basolateral membrane, the ATP or ADP is metabolized down to adenosine. Adenosine, or it can just stay as ATP, but adenosine and ATP then become signaling molecules. You're probably very familiar with the functions of ATP, ADP, and adenosine in terms of energy metabolism. But you may not necessarily be aware that they can act as signaling molecules. And in fact, in the brain, ATP acts as a neurotransmitter, but we won't get into that right now. ATP and ADP bind to their receptors, which ATP binds the P2X receptor and adenosine binds the A1 receptor. You don't need to know the names of these receptors for me, but you will have to know them next year for CPR2. But I'm introducing them here now. These receptors are expressed on the cell membrane of the vascular smooth muscle, the VSM cells of the afferent arteriole. So that's what these kind of orange oval circles are depicting. These are muscle cells of the afferent arteriole. When adenosine and ATP binds their receptors on this cell, that stimulates another series of steps that are kind of in between step 3 and 4 here. I'm not going to go into that signaling cascade, but what happens next is calcium, intracellular calcium, is released inside the vascular smooth muscle cells. And that can transmit a signal through junctions that connect all of the vascular smooth muscle cells together. So now we have a bunch of release of intracellular calcium. That intracellular calcium does a couple of things, whether we're talking about the vascular smooth muscle cells or the granular cells. If it is a vascular smooth muscle cell, it results in constriction of the afferent arteriole. The granular cells will also release renin as a response, or decreases release. It inhibits the release of renin as a response, So 2 things that happen whenever you increase sodium chloride delivery to the macula densa. The end result is you have a decrease in renin release and you have vasoconstriction of the afferent arteriole, both of which serve together to decrease GFR as well as decrease renin release. And what this does is this will slow down. Why is it wanting to do this? Well, we had increased delivery of sodium chloride in the first place. Now we're wanting to kind of slow that back down so that you can kind of compensate. So next, in the next slide, we're going to talk about the opposite thing. What happens if you have a decrease in sodium chloride delivery to the macula densa? Here is the opposite from the last slide, where if you decrease now sodium chloride to the macula densa, this is going to set off kind of the opposite series of reactions. What are things that can decrease delivery of sodium chloride to the macula densa? Well, it can be a decrease in dietary intake. So it can be a decrease in dietary intake, and it can be due to a decrease in GFR, or it could be due to a decrease in renal blood flow. So whatever has happened, there's less sodium chloride being delivered to the macula densa. If there is less sodium chloride being delivered to the macula densa, less sodium chloride is going to get absorbed, which is why there's an X over this cotransporter. If there is less sodium chloride being absorbed, just less ATP and less ADP are released inside the cell and then released to its signaling molecules that would communicate with the vascular and granular cells of the afferent arteriole. There's less ADP around and less adenosine around that's metabolized down, then there's less binding of the receptor. If there's less binding of the receptor, there is less calcium release. It's probably a theme you're catching on here. So if there's less calcium released inside the cell, this is what happens. As opposed to calcium induces a constriction, then less calcium leads to less constriction. If there's less constriction, that means that there is a dilation. If there is a dilation, then
that vasodilation, or a lack of constriction, if you will, means that renal blood flow can go up. Renal blood flow is going up on the afferent arteriole, GFR increases as well. Simultaneously, if there is less calcium being released from inside the granular cells, then there is that lack of inhibition of renin response, meaning now renin is allowed to be released. So before, that intracellular calcium kept renin suppressed. Now we have less calcium-induced suppression of renin. So we have two effects again here. If you have decreased sodium chloride delivery to the macula densa, the two effects is a raise in GFR and release of renin. What is the purpose of these two things? Well, the purposes of these two things is to try to bump up sodium chloride back to the macula densa, because the macula densa, if you kind of keep this in your mind, we just got done talking about how renin is allowed to be released from signaling due to the tubuloglomerular feedback mechanism. Now let's kind of back up again and look at the bigger picture and ask ourselves, rather than what are the steps we need to get to renin secretion, let's ask what all else promotes renin secretion, the direct mechanisms. And we just finished looking at the renin angiotensin aldosterone system being kicked off by a decrease in sodium chloride delivery to the macula densa. That's what we just got done talking about. So that's where you have the NKCC2, you have adenosine involved, you have the adenosine receptors, and intracellular calcium release. Okay, so when all of those go down, because you have decreased delivery to the macula densa, then renin is released. But simultaneously, backing up kind of earlier on in this presentation, we talked about the sympathetics, and the local sympathetics within the kidney can also directly stimulate the release of renin. And it does so through direct activation of the JG cells directly. So sympathetic stimulation upon these JG cells through the beta-1 receptor also directly releases renin. So keep that in mind. There are steps that we can take to release renin as related to the macula densa, but the sympathetics are also involved as well.
This is another slide that shows you an example of what happens in the case of, in this case, decreased renal perfusion pressure. So I mentioned previously, the big question is, okay, if you have less sodium chloride delivery to the macula densa, it results in all these things. Well, what is a reason that you might have less sodium chloride delivery to the macula densa? The answer to that is because, well, GFR bottomed out. And then you might ask yourself, well, what causes GFR to bottom out? And one reason that that occurs is a big drop in arterial pressure. And we call that, specifically as the blood is infusing the kidney, a decrease in renal perfusion pressure. So this is a flow chart that I like, and I want to walk you through. So when you have a decrease in arterial pressure, that decreases hydrostatic pressure in the glomerular capillary. That's that Starling force again. When you have a drop in hydrostatic pressure in the glomerular capillary, GFR drops. When GFR drops, and then this is all written out over here on the right as well, when GFR drops, you have less delivery of sodium chloride to the macula densa. And then a couple of things happen, and that's what was outlined in the previous slide. You're going to have first vasodilation of the afferent arteriole, or a decrease in arteriolar resistance there. And that is mediated not only by the sudden disappearance of ATP and the sudden disappearance of intracellular calcium, but it's also mediated by the sudden appearance of nitric oxide and vasodilators like prostaglandins. So that helps it vasodilate. Subsequently, going on, you have that macula densa-induced secretion of renin, which converts to angiotensin II. angiotensin 2 also has an effect in powerfully vasoconstricting the efferent side. Both of these work together to try to restore glomerular hydrostatic pressure. So what this means here is this dotted line is going back up to the top of this flow chart, and there's this little dash with a circle around it. That is indicating that this is getting reversed. This is getting inhibited. So the reversal of this box means that hydrostatic pressure is trying to be restored in the glomerulus in order to restore glomerular filtration rate. So the question becomes, where is all of this going? So let's take a moment and focus on the afferent and the efferent, to be fair, arterial. First, when GFR transiently decreases, one of the reasons it could transiently decrease is due to a drop in renal perfusion pressure. It could be due to a drop in systemic arterial pressure, or it could be due to a drop in effective circulating volume. That's what ECV stands for here. When that occurs, macula densa is sensing the decreased sodium chloride, and it's going to try to transiently restore GFR by dilating the afferent arteriole and probably constricting the efferent arteriole as well. This momentarily is working to restore GFR back to a stable level. Meanwhile, now this is the connection between the renin-angiotensin-aldosterone system, macula densa, and sympathetics. Meanwhile, if you have a big drop in effective circulating volume, that stimulates systemic sympathetic nervous system. Sympathetic nervous system induces powerful vasoconstriction of the arterioles, both of them. However, afferent is the net more than efferent side. Now, here's something of a possible point of confusion. Sympathetic nervous system also simultaneously works to produce more renin. Now, more renin is going to have the long-term destiny of creating more aldosterone and helping you resorb more sodium. But in the more immediate future, renin stimulates angiotensin 2, which promotes powerful vasoconstriction of the efferent arteriole. So now sympathetic nervous systems have actually kind of done two things at the same time. It is vasoconstricting the arterioles a lot directly, specifically that afferent side, but it's also indirectly vasoconstricting the efferent side via angiotensin 2 as kind of an intermediate step. Now let's go on and see what else we can find. So let's take a moment and pause, because this is a big wait, what kind of a moment. How do you reason through renal physiology with all of these apparent contradictions and things going on at the same time and feedback loops? And it's overwhelming. How do I, as a student trying to understand not only the local nitty-gritty details, but all the big picture purposes that the body needs to keep itself in stable homeostatic conditions? Well, I think that the next series of slides are going to help reinforce the concept of parallel pathways all working together at the same time to accomplish a goal. And sometimes there are built-in contradictions on purpose. I'll highlight those as well. Let's take the case of an integrated response to a decrease in effective circulating volume. All right, so we have this flow chart over here on the right, and at the very top is a decrease in effective circulating volume. Now this could be due to a number of reasons. It could be heart failure, it could be hemorrhage, it could be that you donated blood and lost a liter of blood, or whatever it is. A decrease in effective circulating volume is going to exert what I call the first in 4 parallel pathways that are going to work to try to aka restore effective circulating volume, but also try to stabilize your systemic body response. The first pathway is the stimulation of renin, and we talked through already how renin gets stimulated by a drop in effective circulating volume, the drop in GFR, activation of tubuloglomerular feedback mechanisms, and discussion, communication with the macula densa back to renin itself. And also it's going to work to transiently try to maintain a stable GFR through the more traditional nitric oxide, lack of ATP, adenosine, prostaglandin, all of that kind of immediate signaling mechanism will help to try to restore GFR, but that is not necessarily going to be a long-term solution to a drop in effective circulating volume. This is a big deal to the whole body. So therefore, there are also big deal body-wide responses to it. Sure enough, via the macula densa trying to stabilize GFR, that will in the moment help to protect the glomerulus and protect the kidney, but there's a larger goal, and the larger goal is to also try to correct the effective circulating volume loss. It's going to do so through these 4 parallel pathways. Stimulation of renin. Renin is stimulated by a decrease in blood pressure via signaling from the juxtaglomerular apparatus, decreased sodium chloride delivery to the macula densa through the sensation of the sodium chloride sensor itself, or a decrease in renal perfusion pressure. There are baroreceptors that are in the blood vasculature of the kidney. All of these, any of them, all 3 of them together work to promote renin secretion. Activation of the angiotensin-aldosterone system subsequently releases aldosterone to help promote sodium reabsorption in the distal tubule, but also works to promote angiotensin II signaling very, very locally at the level of the glomerulus to vasoconstrict the efferent arteriole. And together, they work to change hemodynamics in such a way that sodium excretion decreases, or you could say that sodium retention is maintained. Here are the actions that promote angiotensin II release, and then what does the fate of angiotensin II do itself? Of course, angiotensin II continues systemically to create aldosterone, but very locally will vasoconstrict the efferent arteriole, as I said in the previous slide, can enhance the efficiency of the tubuloglomerular feedback entire mechanism, and angiotensin II can feed back up towards the brain to help promote the thirst mechanism and continually secrete additional ADH. And we don't really go into that too much, but what I really want to highlight for you here is that it vasoconstricts the efferent arteriole. The next step, or the second of the 4 parallel pathways that work to create a decreased effective circulating volume, is the sympathetics. So systemically, the sympathetic activation will kind of affect the entire renal vasculature, as it would pretty much the entire body-wide vascular system, and that it will increase resistance of the renal vasculature. And as we discussed in previous slides, there are targets of the renal vasculature that are probably more affected than others, but the effect in general is to increase renal vascular resistance, help promote increased sodium reabsorption, as we mentioned earlier, through those activation of the sodium potassium ATPases in the tubule epithelium, and then indirectly enhances renin release through activation of the JG cells. The third signal of the 4 parallel pathways is the release of ADH. ADH, of course, comes from the pituitary via signaling from the hypothalamus. And the things that trigger ADH release themselves is a decrease in plasma osmolarity or a big decrease in effective circulating volume. The fourth and final effect of a decrease in effective circulating volume, and the fourth action to try to correct it, is an inhibition of atrial natriuretic peptide and an inhibition of that ANP release as well. So as you can see, that all 4 systems work in parallel and together with one big systemic effect, and that effect is to try to correct a drop in effective circulating volume, restore that effective circulating volume, and restore blood pressure back up to normal. It does so through things that work to retain more sodium. And in the short term, in the very, very moment by moment, the glomerular filtration rate might adjust to try to protect the glomerulus, but the long-term goal is to retain sodium and restore blood volume. This is another flowchart that I like, even though it looks busy. It goes through the same kind of four main parallel effects that work to correct a drop in effective circulating volume, but it does throw it with a little bit of a different flow to it, a little bit of a different language that you'll see here. And I like this one too. I like the previous one, but I also like this one, so I wanted to show it to you. And that is when the GFR decreases through a drop or due to a drop in effective circulating volume, whatever reason that is, you want to promote sodium reabsorption in the proximal tubule. You want to promote sodium reabsorption in the distal tubule and collecting duct, and therefore allow for water to follow it. And that water following sodium is what's going to help plump that effective circulating volume back up to normal. However, this correction, this entire process can take hours or days, and it takes a while simply because the hormonal system is kind of slow. It takes a little bit of time for the signals to circulate throughout the entire body, for increases in transcription and translation and additional insertion of transporters into the membrane. That stuff just takes a little bit. So in the meantime, the macula densa is working at the instantaneous second by second moment to try to protect GFR. And that, I think, is where the apparent contradiction lies in trying to reason through all of this renal physiology. I will summarize by reminding you of the mechanisms that work to regulate renal hemodynamics, and they are the intrinsic and the extrinsic mechanisms. Intrinsic mechanisms being autoregulation and tubuloglomerular feedback. Tubuloglomerular feedback is essentially the macula densa stuff. Their main purpose in existence is to protect the glomerulus and stabilize GFR, whether that GFR is going up or going down transiently, moment by moment. Extrinsic mechanisms are the large systemic sympathetic nervous system, large, big fluxes and hormones that circulate throughout the entire body, or even the composition of blood itself, and I don't even really go into that so much in this class. But their main purposes, the extrinsic renal hemodynamic regulations, are to correct body fluid disturbances and stabilize blood pressure, whether that blood pressure goes way up or that blood pressure goes way down. And interestingly enough, the intrinsic mechanisms don't necessarily know what the extrinsic mechanisms are trying to accomplish. And sometimes these two systems will fight each other because they don't necessarily know what the other one is trying to do. The macula densa lives for itself. It only cares about sodium chloride delivery to the distal tubule. And if there are a number of things that are perturbing that, it will work to correct it, even sometimes in the face of what seems to be working against the extrinsic mechanisms. Extrinsic mechanisms can also, therefore, work to correct body fluid disturbances and stabilize blood pressure, sometimes to the sacrifice of the kidney. And let me give you an example of that. An example of that is during times of extreme hemorrhage, the sympathetic nervous system and your entire body can go into such a jolt of shock that you will want to protect more vital organs from blood loss, like the brain and the heart, and divert blood away from even the kidney or the gastrointestinal system or your muscles or these other kind of non-vital organs that aren't necessarily vital for life in the immediate. So in that case, renal intrinsic hemodynamic mechanisms, they just go right out the window and they don't really accomplish much because you're not, getting any blood to your kidneys anyway, because it needs to go to your brain, otherwise the body might expire. So that concludes this video. I hope it helps clear things up. I understand that this can take a little bit of time to conceptualize and walk through. I like the idea of utilizing flowcharts to help keep your logic reasoning step by step. Keep an idea in your mind as you're going through this of the temporal aspect to everything and what is the short-term goal, what is the long-term goal, and then think to yourself, what is the immediate next step that could be occurring to accomplish those goals. You'll need, in order to answer questions and get through your test questions and boards and beyond, you'll need to have enough details in order to understand that. But just keep in mind when you're reading those things that focus on the moment and focus on the goal of whatever the question is being asked, the vignette, and that's my recommendation on how to approach this stuff. Continue to let me know if you have additional questions, and I will continue to do everything I can to help. Thank you very much. So we have one last thing to calculate, and that is the fractional excretion. Fractional excretion is essentially telling you what percentage of what that, however it is, or whatever it was that got filtered, what percentage of that actually gets excreted. Okay, so this is going to take into consideration glomerular filtration rate, clearance, and then an idea of what the ratio of what gets excreted to what is filtered. Okay, so let me give you an example. To calculate fractional excretion, that is the amount of something that gets excreted divided by the amount of that same something that was filtered. Okay, so if you have a value of 1.0, that means that 100% of whatever got filtered got excreted. 0.9 is 90% of whatever got filtered got excreted. Okay, so if 90% of what was filtered gets excreted, something had to happen to that outstanding 10%. That outstanding 10% means that 10% of it got reabsorbed. Okay, if you have a fractional excretion of 1.1, that's 110% of whatever got filtered got excreted. So hang on, you have more showing up in urine than what was filtered. Where did that extra 10% come from? Well, that means that 10% of what got excreted must have been additionally secreted from the peritubular capillaries back into the tubule system. So we had a little bit of extra addition of substance going on there. So to calculate this, this is calculated via the following: U times V divided by P times GFR. If you assume GFR is the clearance of creatinine, you can insert the clearance of creatinine here, rearrange your equation, and you get this one in the big box, which is U times X times the plasma concentration of creatinine divided by P of X times urine concentration of creatinine. So let's say I wanted to ask you, what is the fractional excretion of sodium? You would need the urine concentration of sodium, the plasma concentration of sodium, as well as the plasma and urine concentration of creatinine in order to solve that problem.